All right, one more. Here's an example out of Hibbeler's 14th where we have, this is sort of like an application. I like this one better than the examples that are in Beer-Johnston. Don't tell them. We're going to determine the magnitude of the moment, right, of this force about the axis OA, right there. Okay, so there's this, we can make a new axis that goes between O and A, and we want to know what kind of moment is going to be spinning about that because of this force. But this force is not applied at that place. So what we have to do is find the moment about O and then project that moment onto that axis so we could find only that one that's twisting about OA. I guess it's kind of practical. I don't know if it's practical or not. Maybe that's saying too much. But the first thing that we'll do is to find, we're going to find, let's see, I'll use my little handy dandy ruler. We're going to find, and they kind of look a lot like each other. That's unfortunate. We're going to find that position vector. We also want to have this position vector right in there, right? So this is the axis that will eventually, we want to see how this thing is spinning about, right? So how much moment is being placed about this axis OA. But first we need to get a moment about O from right there. So this is going to be the RB with respect to O, and this is going to be the RA with respect to O that we're trying to find. So first off, RB with respect to O is going to go, and once again, they messed around with us by having our X, Y, and Z. I really want to change those, but we're going to keep them the same. So in the X direction, we're going 0.3, positive 0.3, and that's I. And then in the Y direction, we're going a positive 0.4. And then in the Z direction, we're going to go a negative 0.2. Did I do that right? Yep, negative 0.2. And then we only need that. We don't need the direction cosine, but we're going to need the direction cosine of this guy right here. So we're going to do this, and it's going to be very similar because we do go over 0.3 in the X direction. We still do. And in the Y direction, we do that 0.4, but it's on the same plane as the the O right there. So it's going to be 0 in the K direction. So we take a absolute value, or magnitude I should say, and we get 0.3 squared plus 0.4 squared. Is it going to equal 0.5 squared? Yes, it is 0.5. So it's a 345. I try not squared, but so okay. And so the direction cosine of A with respect to O right here. So the direction cosine that makes a line with that right there is just going to be our 0.3 divided by 0.5. Right? Is that true? I plus 0.4 divided by 0.5, J, right there, and there is nothing in this direction right there. So we end up finding it's going to be 0.6 I plus 0.8 J plus 0 K. That's awful K. All right. So let's, we got everything we need. We're given what this force is going to be. So the moment about O is going to be RB with respect to O crossed with F. So let's make it I, J, and K. And R that we just found up here is 0.3, 0.4, and negative 0.2. And the vector is 300, I don't know why I'm using parentheses now, negative 200, and 150. So let's take the determinant of that. We have 0.4 times 150 minus negative 0.2 times negative 200 I. We're going to have enough room? No. Okay, I always forget this one. This one's negative. Minus. And so we have 0.3. We're going to go from here to right over there. Times 150. And then minus 0.2 times 300. J. And then lastly, we're going to have the cross of these two. So the determinant of that smaller one. So it's 0.3 times negative 200 minus 0.4 times 300. And that's going to be K. So we are left with, for the moment of O, 20. If we do the math right there, it comes out to positive 20. Do the math right here, we get a negative 105. And then we do the math over here, and we get a negative 180. I'm assuming 0.0 right there. Okay. And I'm assuming that's 0.00. And these are Newton meters, because we had newtons, and all their distances are meters right in here. So if we want to find MOA, we take and we dot our A with respect to O, dot that with our MO. And so each of these is going to be multiplied. So we go 0.6 times negative 105, then 0.8 times our, what did I just do that for? 20. It's tired, right? 20. There's an X with X right there. And then this is going to be times the negative 105. And then 0 times our negative 180. So the answer to this is simply going to be a negative 72 Newton meters. And I think there's other examples where we could try to see why we're doing this. There is a good question of why we're doing this, but maybe we want to see why this thing would try to spin about an axis that's drawn from 0 to 72. There's a couple problems I kind of like where there is like a pipe or something like so I had made one where we see like there's some kind of pipe, and let's say that there's like a fitting right there, and this pipe is screwed into that fitting, into this larger pipe right in there, and we have a force that's coming off at some angle right to there, right? So what we want to do is find the moment that's being generated by this thing right here, and then find out, project it onto this pipe so we could see how much, if it's going to unscrew, like what part of that moment causes an unscrewing of the piece, right? Because we're probably going to find a moment that's going to be, when we get the actual moment in between here and here, due to this force, we're going to get it, in terms of all of these directions, a moment here, here, and here. But we really care about what that moment is happening right along that line of the thing. So then you could just project it along the known distance right in there. There might be a more straightforward way of doing that, but I don't know what it is. But I think it's this is a better example than the one that's in the book, I think. But this is maybe more something that I can kind of give you some justification for doing this, as opposed to just playing around with the math. So it's time to go to bed. It's 9:30. It's 8:44 right now. You can see on the clock that's down there, p.m. on February 18th, and 10 minutes. 9:49, 9:50. That's how long this thing is. But good night.